Thanks for joining me. We're about to go through and do some practice problems. Now, you know we've heavily invested in this. In particular, if you look somewhere down here, you'll discover there's a pause button. That's an amazing feature of this video. You see, what you can do is once you see a problem, pause. Think about how to do it. Better yet, do the whole problem. And then, once you're ready, unpause. And even if you can only do part of it, do as much as you can. The more you can do by yourself, the better you'll get. All right, let's begin. Let f be a differentiable function defined at each x, and x goes from -6 to 3, and f prime of x is given in the graph. So this is not f of x. Notice it's very explicit here. This is f prime of x. Okay, we're going to come back and mention some things about that, so make sure you keep that in mind. This is the graph of the derivative, not the graph of the function. So, we're going to use this graph to answer the questions and to justify our answers. Okay, so we don't have a lot of space because there's a lot of problem, but we'll try our best to fit it in here. All right, so let's see. A. Identify the critical points of f and classify each critical point as a maximum, a minimum, or neither a maximum nor a minimum. Okay, so how can we do this? Well, let's think about what critical points are. So when we're talking about critical points, we're going to key off of the derivative. And we're looking for two things. Where is the derivative undefined? Where is the derivative 0? Now, looking at this picture, you might say, oh, these kind of points here, look, the derivative is undefined. No, because remember here, this is the derivative graph, right? This is not the graph of the original function. Where is the derivative defined? It's defined everywhere, because there's always a value here. So every point has a derivative, so the derivative is not undefined. So where are the critical points going to be? Well, the critical points are going to be where the derivative is 0. In terms of the picture, being 0 means that we're crossing or touching the axis. So there are 3 critical points. So for part A, we're going to say our critical points, and there's a lot of things we could say. So critical points are where f prime equals 0. So they happen at x equals -5, -1, 2. And now we're going to say what kind of critical point, right? We've identified them. And this is the justification. We want to classify. So we're going to do a first derivative test. And when you're doing first derivative test, you draw your number line and you mark the locations. So it's these locations here, right? -5, -1, +2. Now, when we're doing first derivative tests, we're looking at the first derivative. This is the first derivative. And what's our question? What's the sign? We saw the sign, and it opened up our eyes. We saw the sign. Right? So we're just asking positive or negative. So we're looking here, and we're saying, okay, if I'm below -5, am I positive or negative? Positive. All right, so here we're going to make some notes. F prime positive. If we're between -5 and 1, -1, are we positive or negative? We're negative because we're down here. So f prime less than 0. If we're between -1 and 2, so here, positive or negative? We're negative. We're down below. Okay, so f prime, again, less than 0. And if we're above 2, so we're in this stretch, are we positive or negative? Positive. We're up these stairs. So f prime is greater than 0. So we're like, oh, okay. Now, that tells us increasing, decreasing. So we see we're going increasing, then we're going decreasing, right? Because positive, negative. Here, we're decreasing, then we're decreasing. Negative, negative. And here, we're decreasing, then we're increasing. So this is the first derivative test. We're looking at and saying, what's the behavior on either side of the critical point? So, what's our conclusion? Well, the answer, -5. If we go up then down, we're going over the hill. So -5 is a local max. How about -1? We're going down then down. Okay, what does that tell us? It tells us we're at a local, well, I was about to say local something. No. It tells us we're neither. Neither. All right, be careful. And at 2, here we're going down and up, right? Zoop, right? Zoop. You can see that? Going zoop. You don't have to make the noise, but you can see that, going down then up, down then up. So we're bottoming out. So that means set 2 is a local min. Okay, good. That's part A. Good, good. Now, part B. Identify the intervals on which f is concave up or concave down. Identify the inflection points of f. So, how do we figure that out? Well, we think about what concavity relates to. Second derivative. How is the derivative changing? So he's like, oh! So if I understand how the derivative is changing, that gives me the concavity. So in particular, we can say for part B, we can say, look, where f prime is increasing, that really means f double prime is positive, which really means concave up. And similar, where f prime is decreasing, going down, that says f double prime is negative, and so concave down. All right. So we're looking for where does the function change behavior in terms of going up or down. And when I talk about the function, I mean this function. So we say, well, we're going down until -3. Then we go up until -1. Then we're going down until 1. And then we're going up. So if we look at, again, the number line, but now we're going to mark -3, -1, and 1. These are our 3 points. And you might notice that they also correspond to where f prime have local maxes or mins, and we'll come back to that in a second here. Okay, so we're going to do the same thing we talked about before. So we have f double prime. What's happening here? We're going downhill. Going downhill means we're negative. Uphill means we're positive. Downhill, negative. Uphill, positive. Okay, so we now know the signs. We can see the signs for the second derivative, and we're ready to answer our questions. Okay, so where are we concave up? So for that, concave up, we're looking for our intervals where we have positive second derivative. So -3 to -1, and from 1, and really we're going 1 to 3 because we stop at 3. So 1, 3. Concave down. Okay, so it's before -3. We're starting at -6. So -6 to -3, and from -1 to +1. Okay, so there we go. Those are our intervals. Where are the inflection points? Inflection points are where we change concavity. And where is that? Well, we change from negative to positive at negative 3, positive to negative at negative 1, and negative to positive at 1. So these are all inflection points. So we have 3 of them at negative 3, negative 1, positive 1. And in terms of f prime, these correspond to maxes and mins in f prime. So where you see a max, a local max or a local min, that's going to be an inflection point, and vice versa. All right, so there we go. We found the critical points, we classified them, we figured out the concave up, concave down, and we found inflection points. So we did A, and we've done B. And then we have the bonus round, but it's not graded. Okay, whew, good. So, but we'll still do a quick, rough approximation. All right, let me grab a piece of paper because we're pretty full already here. But don't worry, we always have more paper. And we'll cover up this part here. And I want to mark some information. So before we get going, what I want to say is what's happening in terms of the derivative and the second derivative. So if I see f prime is positive and f double prime is positive, increasing concave up. All right, that says our basic shape looks like that. All right, we're going uphill and we're getting steeper as we go uphill. If we see f prime is positive, f double prime is negative, well, that looks something like that. So we're going uphill, but we're starting to shallow out. If we see f prime is negative and f double prime is positive, well, now we're going downhill, but we're sort of shallowing out in that sort of way. And if f prime is negative and f double prime is negative, and okay, so we're going downhill and we're getting steeper. So these are your basic shapes, and we're going to keep that in mind. Now, for us, here we have our f prime, and I'm going to sketch a couple of places, and I'm going to mark some points. We have negative 5, and negative 3, and negative 1, and 1, and 2. Now, what have we marked here? We have marked all the places where the derivative is 0 and where the second derivative essentially is 0 or undefined. So we've marked critical points for the first and second derivative. Put another way, we've chopped up our number line now in such a way that in each piece, the first and second derivative has a consistent sign. So we're now going to go through and mark the signs for each interval. So for this first interval, notice f prime is positive, but we're going downhill, so f double prime is negative. Here, we're still going downhill, so f double prime is still negative, but we're now underneath, so f prime is also negative. From negative 3 to 1, well, we're underneath here, so f prime is negative, but we're going uphill, so f double prime is positive. From negative 1 to positive 1, we're still f prime is negative, but we're going downhill, so f double prime is negative. From 1 to 2, f prime still negative, but notice we're going uphill, so f double prime is positive. And now, above 2, we say, we're going uphill, so f double prime is positive, and it's a positive value, so that says f prime is positive. All right, so this is the information we need. All right, now one other thing is we were told f of 0 equals 2, so I'm just going to make a note here, f of 0 equals 2. And this is going to be a really, really rough sketch. So you could say it's a bit sketchy. but that's okay. That's what they want us to be, right? They want us to give us a sketch. And so we say, okay, f of 0 equals 2. Let's say this is 2. Now, what's happening? We see negative, negative. What is that telling us? It's telling us that we're behaving like this. Okay, so we're going downhill. And we're sort of like going downhill a little bit steeper. So we're like, okay, so we're going down. And, all right, what happens in the next interval from 1 to 2? Well, we're still going down, but f double prime is positive. So we're now in this situation. So we're sort of turning the corner. All right, so there was our inflection point. Now here at 2, if we went back to the diagram, we see that's where the derivative is 0. So it actually is going to be leveling out. So here is 2, it levels out. And then what happens? We're going f prime and f double prime are both positive. So we're going to be doing something like this. So there's that basic shape. Okay, so that was going forward. How about going back? So at negative 1, and notice again at negative 1, derivative is 0. So we become flat. Okay, so that's good. We're flat. Now, below negative 1, from negative 3 to negative 1, what's happening? We have f prime is negative, f double prime is positive. So we're looking like this. So, okay, so that says we're coming in. And that's okay, because we know negative 1 isn't a max or a min, but has 0 derivative. So it's this sort of zoop, zoop kind of thing. It's like x cubed looking behavior. All right, and now that'll take us over to, say, negative 3. And what happens at negative 3? Well, both are negative. Okay, so we're looking like this. And so we have this inflection point. And then below that, here we are at negative 5. What do we see? Well, we see f prime is positive, but f double prime is negative. So we're like this. And if we go back, we'll see that, hey, 5 is where we zero out. And so, again, we zero out, which means flat tangent line, and we have that shape, so we're going down again. And so there we go. There's a rough sketch. Up, then down, and then we level off, go down, level off, back up. There's our function. So this is a rough sketch for the function f of x. All right, I don't know how much bonus we're going to get for that. I don't think we're going to get really anything, but it's nice we can do it. All right, good. Well, off to a great start. Yeah. Find and classify the critical points of the function x to the fifth minus 5x to the fourth plus 5x cubed minus 1. Okay, so what are we looking for? There's no boundary. We're not worrying about anything about boundary. Polynomial, we love polynomial, our favorite kind of functions. Well, maybe flat is our favorite functions, but those are polynomials. So, okay, so we love polynomials. And it's one of our great big themes in calculus, especially in calculus 2. It's like everything comes up polynomial. Okay, so we're not going to have to worry about undefined derivative. So this is going to come down to, where's the derivative of 0? Okay, so we should start by taking a derivative. We have f prime of x, and that's 5x to the fourth minus 20x cubed plus 15x squared and 0. Right, on each one of these, you just follow the rule, right? The power comes down and you take one down. Right, 5 comes down, 5 minus 1 is 4. 4 comes down, 4 minus 1 is 3. 3 comes down, 3 minus 1 is 2. Now, we look at it and we say, or perhaps we say, oh. But we start saying, okay, there's a chance here, right? Because they have things in common. They have 5. That's a common thing. They also have x squared. All right, well, let's do something with that. Let's pull out what's in common. So if we pull out a 5 and an x squared, we'll have an x squared left from the first one. Here we'll be left with a 4. It's a minus 4, and then a single x. And here it will be a plus 3. Okay, well that's looking promising. And indeed, it almost looks like we can factor. And that's because we can factor. All right, well that's a good reason why it looks that way then. So how does this factor? X minus something, x minus something. Two things that multiply to 3, add to negative 4, minus 3 and minus 1, right? X squared, good. Minus x, minus 3x, good. Plus 3. All right, so now what do? We found our derivative, and we want to say, hey, this will tell us something about our critical points. Our critical points are coming when we get zeros. And when we have multiplication, we say, okay, where's our zeros? Well, we have the first term, the x squared term. The 5 definitely isn't causing a 0. It causes a 5. X squared could be 0 at x equals 0. X minus 3 could be 0 at x equals 3. And x minus 1 could be 0 at x equals 1. Now there's a question. We found them. We've finished that step. How to classify? Now, there's two tests called first derivative test, second derivative test. Which one do we use? And does it matter? Well, the short answer, it doesn't matter which one we use. The real question is, which one's better to use? And I'm biased. I tend to try to do the first derivative test if I can. Now, the reason I'm biased towards the first derivative test is because I have the first derivative. And so oftentimes by the time I found the roots, I found a nice way to write it so that I can easily test the signs for the different intervals and figure out increasing, decreasing. I'm also a little bit worried when I go to second derivative, do I get the second derivative right? And then it might be kind of iffy on how to compute the second derivative, especially if you have weird numbers. So this is my own personal bias. If you can use the first derivative test, use it. And if you can't, second derivative test is there. So we will run a first derivative test. We mark our points in order, 0, 1, and 3. And we start testing the intervals. Well, okay, we pick a number for each interval. A number bigger than 3, like 1,000,000, or 4. Either one, I guess. Lots of choices. Any number works. Okay, so here we go. We're going to check each term. Positive, 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 right? 4 minus 3 is positive. 4 minus 1 is positive. 4 squared is positive. Everything's positive. So here we have f prime is positive. Okay, from 1 to 3, 2. Yeah, classic. 2 squared is positive. 5 is positive as well. 2 minus 3, negative. 2 minus 1, positive. So positive, negative, positive. All together, a negative is coming out. Between 0 and 1, I'll split the difference, a half. Okay, half squared, positive. A half minus 3, negative. Half minus 1, negative. Positive, negative, negative. All together, positive again. Now you'll notice I'm not really paying attention to the value because that's not helpful. I'm paying attention to the sign. The sign is telling me uphill or down. So don't worry about, oh, well, what is a half minus 3? Is that negative 5 halves or is it something else? No, just say, is it negative or is it positive? That's all we need. All right, something below 0. How about negative 1? All right, negative 1 squared, positive. Negative 1 minus 3, negative. Negative 1 minus 1, also negative. So we have positive, negative, negative, and that means we're still positive. Okay. So what's happening? At 0, we see before we're going up, afterwards we're going up. All right, well, we'll come back to that. And now at 1, before 1, we're going up. After 1, we're going down, because the signs are telling us. At 3, before 3, we're going down. After 3, we're going up. And now we see, aha, we can read off the answers. So let's write down our final answers. So at x equals 0, this is neither. We're going up, then up. So if you go up, then up, it's neither max or min. Okay, so neither. Neither max nor min. It's still a critical point, but it's just one that's not a max or a min. At x equals 1, what do we see? We're going up and down. Shoom, right? Whoosh. So, what is that? That is a local max. And at x equals 3, we're going down then up. So, what are we forming? We are at a local min. And we've classified, and that's it, right? We found them, we classified them. Life is good. Woohoo! Nice! All right. On what intervals is h of x equals x squared minus 5 natural log of 9 plus x to the fourth increasing, and on what intervals is it decreasing? Okay, so before we get too far into it, we notice it's asking us about decreasing and increasing. These are first derivative type questions. And so we can say, oh, when it says increasing, it's really saying where is the derivative positive, and when it says decreasing, where is the derivative negative. So there's a plan. Let's take the derivative, make sure we understand it, and then say, hey, are you positive or negative? And that'll tell us whether we're increasing or decreasing. All right, so to begin with, a derivative. So what is h prime of x? Well, the derivative of x squared is 2x minus 5, and now you have a log. So how do you take the derivative of a log? Well, it's always a fraction. Whatever inside the log goes downstairs. 9 plus x to the fourth. Now take the derivative of 9 plus x to the fourth, and that would be 4x cubed, and you put that upstairs. And there's the derivative of the log. Okay, so, well, let's add these together. So common denominator, 9 plus x to the fourth. So that would be 2x times 9 plus x to the fourth over 9 plus x to the fourth, then minus 20x cubed over 9 plus x to the fourth. Okay, well, we're almost there. We can now put it all together. We have 9 plus x to the fourth downstairs. Then let's see, what do we have upstairs? Well, we have a 2x times an x to the fourth. So that's a 2x to the fifth. Then we have a minus a 20x cubed. And then we have a plus 18x. Okay, wow. Whew. Yeah, it's a thing. Now, when we're trying to figure out where things are positive or negative, the real thing is where can it switch signs? Those are the critical points. And so we're going to start looking at critical point questions. Now, we see a fraction, and we take a quick peek at the denominator. And we say, can this ever be 0? Well, the good news is 9 plus x to the fourth is always positive, so phew. All right, you don't have to write down phew, but that means there's no division by 0, there's no undefined. So, what's the other thing for us to look for? Well, the other thing for us to look for is what's upstairs. So we say, okay, so now we're going to say we want the h prime of x equals 0, which means that the numerator equals 0. So we're going to focus our energy here for a few minutes. Now, let's see. We have a 2x to the fifth, a 20x cubed, and 18x are all polynomial terms. They all are even, so we can pull out a 2, and they all have a factor of x. So let's pull out a factor of x. So we have 2x, and we have x to the fourth minus 10x squared plus 9. Okay, and now say, how do we factor a quartic, a fourth degree polynomial? Well, the answer is we don't. Or do we? Because it is a fourth degree polynomial, but notice there's no cube terms. There's no x terms. The only powers we see are x to the fourth, x squared, and essentially x0. So let's make some side notes over here. Given that all these powers are even, we could think of this as like x squared squared minus 10 x squared plus 9. Or, just temporarily, think of it as y squared minus 10y plus 9. And now, could we factor that? Yeah, we can, actually. Okay, it factors into what? Y minus 1, y minus 9. Because we need two things to multiply together to give 9, but add to give negative 10. And then we say, okay, so you can check, right? Y squared minus 9y minus y plus 9. But y was a name. It was a substitute name for this quantity x squared. So this is really x squared minus 1, x squared minus 9. But hold on, x squared minus 1, that's famous. We see that one so often, it's sort of ingrained in our souls. It's a difference of squares. So it's like, this is like x minus 1, x plus 1. And in a similar way, x squared minus 9, that's x minus 3, x plus 3. So, what do we have? Well, we have that this becomes, our h prime is 2x, x minus 1, x plus 1, x minus 3, x plus 3. Whoa! That's crazy! But it's true. All right, so now, here, we're ready. And let me plug it in, and we set it equal to 0. Say, where do the zeros come from? They come from the upstairs. We get 0, 1, minus 1, 3, minus 3. Okay, so let's draw the number line. So we have from minus 3 all the way to plus 3. And we just plug in values. The denominator will always be positive, and so the question is what happens upstairs. So if I plug in, say, 4, positive, 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 all positive. So h prime, positive. Suppose we plug in 2, positive, 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 negative, positive, 1 negative. So h prime will be less than 0. Okay, suppose we plug in a half. Positive, negative, positive, negative, positive. 2 negatives. So that makes it positive. Okay, suppose we plug in negative a half. Negative, negative, positive, negative, positive. 3 negatives. So altogether, it's negative. Suppose you plug in negative 2. We have negative, 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 positive. 4 negatives. So that makes h prime positive. And say negative 4, negative, 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 negative. That's 5. 5 negatives. So that makes h prime negative. Okay, so we really have 2 cases, right? Where h prime is positive. So we'll just mark those. And we have where h prime is negative. And so we'll mark those with a different color. And now we're ready to write down our answer, right? Because the question was increasing, decreasing. And what we did was we found out where the derivative is positive and negative. So for increasing, what are the intervals? Well, we have -3 to -1. We have 0 to 1. And we have 3 to infinity. On a side note, personally, I'm somebody who would include the endpoints. There's discussions about that. Should you include it? Should you not? So don't worry about it. We understand that there is disagreement even among your calculus instructors, but we care more about the process. Can you find the critical points? Can you test the intervals? Just make sure you get the intervals. Whether you include the endpoints or not, make sure you get the right intervals. Okay, so decreasing, negative. So that's negative infinity to -3, -1 up to 0, and 1 up to 3. And we're done. Yeah. Let g of x equal log of x squared plus cx plus 25, where c is the constant. Two parts. Part 1. Find the value of c so that the single minimum for g of x occurs at x equals 3. Okay, well, let's think about what's going on here. So there's a minimum, and so that tells us, oh, that's got to happen at a critical point, because the only places where minimums can occur is a critical point. So it's telling us that there has to be a critical point at 3. All right, so let's think about how that could happen. Well, so what we can do is we'll look at the derivative, because the derivative will tell us what's going on. And all right, so it's a log, so write it as a fraction, and you have x squared plus cx plus 25 downstairs. Take the derivative of that, 2x plus c. That's what goes upstairs. Now, what kind of critical points could we have? Well, we could have issues where the denominator is 0, but where the denominator is 0, we might have other critical points. And so the first thing we should try is to say, let's try to look at the critical points where the numerator is 0. Okay, so that's an idea. So we say, well, if we want g prime to be 0, then what that tells us is that we need the numerator 2x plus c equals 0. Well, we want g prime to be 0 at x equals 3. So, okay, so at x equals 3, that becomes 6 plus c equals 0, or c equals -6. Now, let's pause and say, is that kind of okay for the downstairs? It's great for the downstairs. If you think about what's going on, it says, hey, this is x squared minus 6x plus 25. But you could do a completing the square downstairs, and you'd come to the conclusion, this is always positive downstairs. And so choosing c equals -6 is a brilliant choice. There's only one critical point. And then you could say, okay, since it's always positive downstairs, you can even check and say, well, if I choose a very large negative value, I get a negative. If I choose a very large positive value, I get a positive. So we're going down, then up. So it does match with being a minimum. All right. So our value for c is -6. We'll write it down again so that the grader won't miss it, because we want to make sure the grader gives us all the points, right? You betcha. Okay. Part 2. Give the x values for the inflection points for g of x. Now, inflection points, where is that? Well, that's really looking at the second derivative. And, okay, so we say, look, let's write down our first derivative. We know what c is, so that's 2x minus 6 divided by x squared minus 6x plus 25. And what can we do? We're going to take another derivative. So we're going to take the bottom, quotient rule, right? Fraction, bottom times the root of the top minus the top times the root of the bottom. All of that over the bottom term, quantity squared. All right, so what does this give us? Well, let's carefully work this out. So that would be 2x squared minus 12x plus 50, subtract, here 2x times 2x is 4x squared, then we'll have minus 12x minus 12x, that makes minus 24x, and a plus 36. Okay, all right, and well, we still have the denominator squared. Well, that becomes 2x squared subtract 4x squared is minus 2x squared, minus 12x minus minus, well, that becomes a plus 24x, so that becomes a plus 12x, and 50 subtract 36 would be 24, right? Yeah. No, wait, hold on. Let's make sure we get this right. 50 subtract 36 would be 14. Okay, good. We want to make sure we have the right numbers, because otherwise, uh-oh. And we don't want to be in the uh-oh state. Okay, well, let's pull out a negative 2. I always like what's in front of the x squared to be positive, and ideally to be a 1. So negative 2, then it would be x squared minus 6x minus 7. Now the moment of truth. Is there a way to factor this? We would need two numbers that multiply to negative 7 but add to negative 6. I think we can do this. So this would be negative 2. And what would it be? Well, x minus 7x plus 1. Let's check. X squared, good. Plus x minus 7x, negative 6x. Wonderful. And a minus 7. Okay, so downstairs, x squared minus 6x plus 25 squared. Whew. Okay, now, we're ready. We can write down the answer, because it doesn't tell us to justify inflection points, but we're going to actually be very careful here. We're going to check. The denominator, no problems. That's not going to cause zeros. So we say, hey, this equals 0 at two places, negative 1 and positive 7. Now, what happens between negative 1 and positive 7? Well, you can plug in 0. The downstairs is always positive. You get a negative, you get a negative, you get a positive. So we say, g double prime is positive. If you plug in a number bigger than 7, say 10, negative, positive, positive, so you're negative. And if you plus something below negative 1, say negative 100 or negative 2, negative, 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 3 negatives, so you're negative. And you can check. We're changing the signs at both negative 1 and 7, so these are proper inflection points. So, our conclusion, our inflection points are at negative 1 and positive 7. And there we go. We found them. Woohoo! Yes! Huzzah! Huzzah! Ha ha! A farmer has 120 feet of fence with which she plans to enclose a pair of rectangular pens along one side of her barn. The pen is formed by forming a rectangle, one side being the barn and the other three sides coming from the fencing. And some of the fencing will also split the rectangle into two equal pens. Each pen will use the barn as one of its sides. So this is a case where a picture is worth a lot of words. So here's the idea. Here is the barn. And you can tell it's a barn because it says barn. Good clue. And what's going to happen is, well, we want to have a pen to put things. And so we're going to have this structure here. So here is our pen. So there's really, we've taken sort of a rectangle and split it into two parts. Now notice the barn is a natural boundary. So we don't need to use fencing against the barn, but we will need to use fencing on these portions here. All right, so that's the picture. What are the dimensions of the pen to maximize the area? Okay, well, not a lot of numbers here. I see this number. So, okay, so great, 120. Wait, no, that's not a dimension, because we need two numbers, right? So what are we trying to figure out? Well, we're trying to figure out how should we build it, right? Because we could be doing something very silly, which is, build something like this, which is very inefficient. That's wrong. We can kind of tell it's wrong, but of course we could do just as silly and build something in the other direction. So it's like, okay, so how do we get a handle on this? Well, let's label things. We have things that we don't know. What we don't know, and what we're looking for, and that's sort of a clue as to what to label, are the dimensions. So let's label this distance here. This is one dimension, and we'll give it a dimension-like name. We'll call it y, since it's right now in this picture it's going up and down. And then this other length, we'll call it x. Now, what's the area? Well, the area, so what we're trying to maximize is the area, which is x times y. All right, now we have sort of two variables. That sounds like a different class. We're not multivariable, we're single variable, right? We're single. We're single and we're ready to mingle. All right, so how do we get it down to one variable, and how do we use the 120? Well, there's a constraint. So that 120 is actually saying you can't choose arbitrary x and y. You have to be able to build it with what you have available. So what's our constraint? Well, how much fencing do we need? Well, we need x length here, but we don't need anything over there because that's the barn. So we'll need x, and here we'll need y length and y again and y again. So 3y, and that's how much fencing we need, and here's how much fencing we have. So x plus 3y equals 120. Good. So what do we do? Well, let's get down to one variable. And so we can use our constraint. So for instance, we could say, hey, you know what? X is the same as 120 subtract 3y. So then our area, if we replace x, becomes 120 subtract 3y times y. Or if you like, that's 120 120y subtract 3y squared. Nice. And we can even think of this as a function of y. So we've got it down to one variable, our favorite kind, single variable. So what do? Well, we're optimizing, so we're looking for maxes or mins. They occur at critical points, and so we take our derivative. a prime of y. So that would be 120, subtract 6y, never undefined, and well, we can plug in, set it equal to 0, and it says 6y equals 120, or y equals 20. Now, did we find a max? Probably. How do we know? Well, we can run some tests. This is a case where second derivative is super easy. Right? What is the second derivative? It's -6. And if you think about the second derivative test, if it's positive, you look like this, meaning you're a min. And if you're negative, you look like that, meaning you're a max. So yes, we're definitely found a max. We can also sort of test extreme cases. So an extreme case would be if, say, y equals 0. And that just says you're building right up against the barn, no area. Another extreme case is if y equals 40. And that's what you see here. Again, no area. And so, well, some area is better than no area. So this has to be the max. That's another way to reason your way through it. So what are our dimensions? Well, so specifically, we're going to have, if we think of our dimensions, we'll go ahead and sketch it just so there's no ambiguity. We're going to have this length be 20. And once you know that length, you plug it in here. 120 subtract 60 says that this distance here should also be 60. So it's 20 by 60. That's your dimension. And there you go. Aha! We did it! We've optimized. Let g of x equal x times log of x quantity squared, subtract 15x. Find the open intervals on which g of x is increasing and decreasing. Okay, so we see words such as increasing and decreasing. And those words mean things. And in particular, this is telling us, hey, we're after information about the derivative. So we care here about whether the derivative is positive or the derivative is negative. So, okay, great. And I used f, but I should have used g, but that's okay. I can do something like that. All right, so what are we going to do? We're going to take the derivative, see what it looks like, and then we'll figure out where it's positive and where it's negative. Okay, so here we go. We have g prime of x. Well, product rule. The derivative of the first is 1. That leaves us with log of x squared. And then plus the first times the derivative of the second. So the 2 comes down. Log of x to the first times the derivative of log of x, 1 over x. And then the derivative of minus 15x, minus 15. Okay, so that's log x squared. There the x's cancel, so that becomes plus 2 log x, and then minus 15. Interesting. Interesting. Notice it feels kind of like a quadratic, right? Think of it for a second. It's something squared plus 2 something minus 15. Suppose you saw that. Could you do something? Does it factor? Can you think of two numbers that multiply together to give negative 15, but if you were to add them, would give you a positive 2? I think we can do that. Let's try y plus 5, y minus 3. What do we have? Y squared minus 3y plus 5y. That's 2y. And minus 15. Whoa. Okay, so g prime of x, which looked terrible, is actually a quadratic. It just happens to be a quadratic which uses the log function. And this factors into log of x plus 5 times log of x minus 3. Okay, now some questions. Is this ever undefined? Oh, sure. If x is 0 or negative, we're in trouble. But we're also in trouble with the function. See, the function, it doesn't explicitly state this, but we can state it, is there's this assumption here that x is greater than 0, because it doesn't make sense if x is less than or equal to 0. So we say, oh, okay, all right. Now, you might say, well, okay, this term, if we're thinking about then where x greater than 0, these terms are defined. Okay, great, great. No undefinedness. If we set this equal to 0, say, okay, well, this would say log of x equals 3. And okay, that seems reasonable. But what about this one? Log of x equals negative 5. Are you allowed to have a negative output from log? Yes, that's perfectly fine. Negative input? No. Negative output? Sure. So make sure, make sure you understand the rules, right? Logs can have negative outputs. And if you get a negative from out of the log, it means that you're taking the log of a very tiny number. So those are the logs of our values. So what are our values? Well, we would take both sides and raise it to the e power. X equals e to the minus 5, and x equals e to the power 3. All right, so here are our values. Now, we can mark the 2 points, e to the negative 5, e to the 3. And there's also this sort of implicit 0, because we can't go negative. So, where can we pick some numbers? Well, between e to the negative 5 and e to the 3, you can just think about, pick something between negative 5 and 3. E to the 0. Beautiful choice. That's 1. Log of 1 is 0, so you get 5, and here, negative 3. Positive, negative, so g prime is negative. Now, pick something bigger than e cubed. A gabillion, a million, just a huge number. Huge number. Log of a huge number is big, so you're going to get a positive and a positive, 2 positives. So here, you're going to get g prime greater than 0. Now, what's something below e to the negative 5, but above 0? Well, you can just think of it as like e to the negative 6, right? And log at e to the negative 6 would be negative 6 plus 5, which is negative, negative 6 minus 3, which is negative, and so we are positive. And now we're ready to write down our answer. We found our derivative. We figured out how to factor it and say, oh, okay, we know where the zeros were. We figured out the signs, and the signs tell us how we're increasing and decreasing. So, final answer. We are increasing in the following intervals, namely from open interval 0, e to the negative 5, and open interval from e to the 3 all the way out to infinity. And where are we decreasing? Well, a single interval, namely from e to negative 5 up to e to the 3. And there we go. Woohoo! Nice! Let's keep this energy going. I like this vibe. Find all inflection points for y equals e to the negative 2x squared plus 10x. And that 10x is upstairs inside the exponential function. And determine the intervals where the function is concave up and where the function is concave down. Okay, so, now, what do we see here? Well, we see a couple phrases, right? We see things like inflection points and concave up and concave down. And we say, oh, all of these, they're coded messages. Well, they're not really heavily coded. This is telling us that we need to look at our second derivative. So y double prime. Okay, so now we know where we're going. We're going to look at y double prime, and in particular, where do we have y double prime greater than 0? This is the same as saying concave up. Whereas y double prime less than 0, this is the same thing as saying concave down. And where we flip between up and down, that's our inflection point. Okay, so we know our future. Derivatives, here we come. So we start. We say, well, y prime, since it's an exponential function, the derivative of exponential functions are pretty clean. Namely, it's the exponential function again, so e to the minus 2x squared plus 10x times the derivative of the exponential function. In other words, chain rule. So, negative 4x plus 10. All right, that's the derivative of the upstairs. So for the second derivative, product rule. So we'll start by taking the derivative of the first, and that's e to the minus 2x squared plus 10x. It's the exponential function times the derivative of the upstairs. Okay, so that's the derivative of the first term times the second. All right, a little bit of deja vu, so be careful. And then add the first, e to the negative 2x squared plus 10x. I'll just put that in brackets, times the derivative of the second, which is negative 4. Okay. Whew. Good. So we've now successfully found y double prime. What's next? Well, we got to work with it. So the next thing is, and this is where you put most of your energy, right, is to rewrite it. You got to use your tools, your algebra, to help rewrite things. Just use algebra. We see they both have that exponential function. We can pull it out. And so that's our first plan, right? So we have in the front e to the minus 2x squared plus 10x times. Now here, let's multiply it out. Okay, so minus 4x times minus 4x, that's 16x squared. Then we have minus 40x, so that's a total of minus 80x. Then 10 times 10 is 100. But don't forget, you're also subtracting 4. So it's 100 minus 4, making it plus 96. Okay, now we look at these numbers and say, do these numbers have anything in common? They all have 16 in common. So we'll factor the 16 out. Wow, it's almost like they planned for nice things to happen. Because they did. Because they want us to enjoy the beauty of math, right? Math is beautiful. And isn't it cool? Oh, it's just beautiful. Okay, so 16 times 5 is 80, so that makes a minus 5x. 16 times 6 is 96, so that's a plus 6. And x squared minus 5x plus 6, well, by golly, if it doesn't factor. And how does it factor? X minus 2, x minus 3, right? X squared minus 3x minus 2x is minus 5x plus 6. All right, good, beautiful. This is lovely, lovely stuff we have going on here. Okay, so now, are we ever undefined? No. This is great. We love this. Are we ever 0? Maybe. Well, what happens? Well, this exponential function, remember, the exponential function is an incredibly optimistic function. It's always positive. It's a happy function. So it's never 0. So it's like, cool. So that's not causing a 0. The 16 is always 16. So we say, okay, that leaves us 2 places. X minus 2, now that can be 0 at x equals 2 and x minus 3, and that can be 0 at x equals 3. Okay, so at this stage, time to draw ourselves a number line, and we'll mark 2 and 3. And now we're going to test. And so we say, okay, let's pick some values. Well, let's pick a value above 3. Let's say 4. We get positive, positive, because we know we're always positive. 4 minus 2 is positive, 4 minus 3 is positive. Everything's positive. So that tells us that y double prime is positive. Okay, how about between 2 and 3? 2.5. Positive, positive, negative. So one negative, multiplying it all together, makes that negative in that interval. Okay, something below 2. 0. Choose convenient numbers, right? Positive, negative, negative. Multiply it together, we're all positive. Okay, so now we're ready to mark things. So, note that at 2, we do flip the sign, and at 3, we flip the sign. So that says, aha, these are proper inflection points. Now, just because the second derivative is 0 does not automatically make something an inflection point. It makes it a potential inflection point. You have to say what's happening on both sides. So, our answer, our inflection points are at x equals 2, x equals 3. Our concave up, where are we having positive concavity? Well, below 2, so that's from negative infinity up to 2, and above 3, so from 3 up to infinity. And where are we concave down? Well, between 2 and 3. And there we go. That's the answer. We did it. Yes. Ha! Wah! Wah! Yeah! A rectangular box with a square base is to be made where the material for the sides and the lid cost $1 per square foot, and the cost for the bottom is $2 per square foot. Find the minimum cost to make a box with a volume of 96 cubic feet. Verify that the cost is a minimum. All right, so let's think about what's going on. We have a rectangular box, but it's not just any rectangle. So we have, it could be something tall, but the important thing here is that we have a square base. And of course, if you have a square base, you have a square top. And there's 2 different types of material. So the bottom material is a little bit more expensive, and that kind of makes sense, right? Because if you're the bottom, you have to support what's in the box. You know, it's the age-old question. What's in the box? What's in the box? And so you say, okay, so for this, the base, it says it's an expensive material, $2. But on the other hand, you've got your sides, and you've got your 4 vertical sides, right? And then, of course, you also have your top side. And so for these pieces here, we say, okay, what do we see? Well, this costs $1 per square foot. All right, so we have ourselves a picture. And now we want to figure out what's going on. Well, let's see what we're trying to do. We're finding a minimum cost. Now, notice we're trying to find a minimum cost. So this is optimization. So we're trying to optimize. Now, what are we trying to optimize? We're trying to optimize cost. So we should write a formula for cost. And if we think about it, we have a rectangular box. Now, normally a box, there's 3 dimensions, right? Length, width, height. But it's a square. So that says that downstairs part, the length and the width, are equal. So we can mark that, right? We can say, okay, so we have x, x. These are our 2 dimensions downstairs, and then the height is y. So our cost, well, the bottom costs $2 per square foot. Now the square footage and the bottom is x times x. So the cost is 2x squared. This is for the bottom. And now plus the rest of the cost is 1 per square foot. Now, if I pick one side of the 4 sides, I have x by y. But there's 4 sides, so it's 1 times 4xy. So these are the 4 sides. Then plus the top is another x squared. Okay, so that's what we're trying to optimize. Okay, good. But there's a constraint, and that's actually useful for us because right now we see 2 things, x and y. We want to get down to 1. One variable to rule them all. So, how do we do it? Well, there's this number we haven't used yet, 96 cubic feet. And so that's our constraint. And in particular, we say, okay, so if you multiply these dimensions, you get our volume. So our volume, which is x squared y, is 96. All right, so good. Now, how does this help us? Well, we can now solve for one of the variables. And so in particular, since there's just a single y here, we could say, hey, this is the same as y is 96 over x squared. So let's now use that in our cost. So where are we at? We can get our cost in the following form. 2x squared plus 4x times 96 over x squared plus x squared. So I'm just replacing the y. And now, since there's one variable, I'll think of it as just a single variable. And before we take any derivatives, let's clean it up. 2x squared and x squared. All right, that's a 3x squared. And here you can cancel an x. 4 times 96 is a number. Yeah, it's definitely a number. Do you need to know it exactly? Let's hope that we'll simplify later. So I'll leave it as 4 times 96 and hope that something simplifies later. And we'll write it as x to negative 1. Right? It's 1 over x, x to minus 1. That's more calculus friendly. So we're taking a derivative. Derivative of 3x squared, 6x. Derivative of 4 times 96, x to the minus 1. Well, okay, you can bring a minus 1 down, so minus 4 times 96. Then that's x to the minus 2. Now, this is undefined at x equals 0. However, at x equals 0 is a very uninteresting box. Because what do you have? You have 0 width, 0 depth, and you'd have to have infinite height to get your volume. And so it basically, x equals 0 is just physically impossible. Okay, so we know it's not coming from x equals 0. All right, well, so that says the other place we need to look is, where is it? 0. Where's this derivative? 0. Okay, so we're going to set this equal to 0. All right, well, that leads us to 6x is 4 times 96. And by the way, 96, I can't help but notice there's a factor of 6 here. That's the same as 6 times 16. Interesting. And x to minus 2 is 1 over x squared. So we can move the x squared across, and we can divide it over by 6. And if we did that, we'd have x cubed. The 6's will cancel, and 4 times 16 is 64. Ah, this is looking really good right now. So x cubed equals 64. So that tells us that x is the cubed root of 64, which is a 4. Good, 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 good. Now, what about y? Well, do we need y? We could find it. 96 divided by 16 is 6. But do we need it? See, sometimes we do, sometimes we don't. So let's see what the problem actually asks us to find. It says, find the minimum cost to make a box with a volume of 96 cubic feet and verify the cost as a minimum. So we don't have to find the dimensions. Sometimes you do, sometimes you don't. Pay attention. So what do we do with this 4? We plug it in to our cost function. So our cost at x equals 4 would be c of 4. That's 3 times 4 squared plus 4 times 96 times 4 to the minus 1, which is 1/4. Well, that's convenient for us. The 4's cancel. 3 times 4 squared, that's 3 times 16, that's 48. And then we have 48 plus 96. And if you add 48 plus 96, that'll get you up to 144. And since it wants units, well, it didn't ask, but we'll throw them in. $144. Now, are we done? Not quite. We have found the minimum cost. We haven't verified the cost is a minimum. Now, we just intuitively know that if we're looking for a minimum and we find one candidate, that's got to be it, right? And it is. It's got to be that. But the graders, they don't like the idea of like, yeah, we know it too, but why? So let's apply a test. So what test should we apply? Well, I'm partial to first derivative test. So to verify it's a minimum, here we go, verifying it's a minimum. We're going to do first derivative test. We say, look, there's just a critical point here at 4. And pick a number less than 4. That's easy to work with. Let's say we pick something like 1. Okay, if I plug in 1, I get 6 minus 4 times 96. So that's a big number I'm subtracting. So that says what? Our C prime is negative. Now pick a number bigger than 4, like a billion, right? There's no restriction. 6 times a billion is huge. A billion to the minus 2 is tiny, basically 0. So we see here C prime is positive, and so by our first derivative test, we see that 4 is a min. Right? Because we're going down, and then we're going up. So there's our verification that the cost is the minimum. So if it asks you to verify, throw it into either the first derivative test or the second derivative test. Or reason through it. But really, first derivative test or second derivative test, that's what you're looking for. And so yeah, we're getting pretty good at these optimization problems. You could even say that we're like Optimus Prime. Find the point on the line y equals 3x plus 7, whose distance to the point 6, 0 is smallest. Hint, find the minimum of the square of the distance between 6, 0 and a point on the line. Okay, so let's see if we can't sketch our situation here. So we have here our axes, And we have 3x plus 7. So here's 7, and a slope of 3 means it's pretty steep. So here's our line, y equals 3x plus 7. And then we have a point, and it's at 6, 0. So it means we've moved over 6 in the x direction, and we have this point 6, 0. All right, so where are we going with this? What are we trying to do? Well, there's a whole bunch of points on this line. In fact, there's infinitely many points. And we're saying of all the points on this line, which one is nearest to 6, 0? Okay, so let's think about it. If I have a point on this line, it looks like it's just eyeballing it. It looks roughly there. I don't know exactly, but we will. What does a point look like? Well, normally a point looks like x comma y, right? Well, but we can, instead of x comma y, we know what y is. So a point on the line looks like x comma 3x plus 7. So I want to say, of all the choices for x, which choice for x gets nearest to here? So we're going to minimize the distance. But we're going to be smart, because distance normally has what? A square root. So distance, let's write down the generic formula. It would be the square root of, then you take x, subtract 6, and you would square it, and add 3x plus 7, subtract 0. And you would square that. And now our goal is to make this small. But we're going to think about the square root function. The square root function has this beautiful property. It has lots of beautiful properties. But the one in particular that we need here is, if you think about the square root, it's what we call an increasing function, which means if your inside is bigger, your output is bigger. And in a similar way, if your inside is smaller, your output is smaller. So how does that help us? Well, it says if you're trying to optimize the square root of something, just optimize what's on the inside. So if you want to make it as small as possible, make the inside as small as possible. If you want to make it as large as possible, make the inside as large as possible. So we can focus our energy on this part. Why is that good? Because we don't have to worry about a square root. And square roots can get messy. So we're going to optimize the following. Optimize the square of the square root. So x minus 6 squared plus 3x plus 7 squared. And we'll call this here f of x. Okay, well, let's take f prime of x. That would be chain rule 2, x minus 6 to the 1 times the root of the inside, which is 1. And then here, 2 comes down, 3x plus 7 times the root of the inside, which is 3. All right, well, let's clean it up a little bit. That's 2x minus 12. 2 times 3 is 12x. All right. 2 times 3 is 6 times 7 is 42. Let's see, is that right? Yeah, good. All right. Oh, wait. 2 times 3 is not 12. 2 times 3 is 18. Yes, there we go. That something felt off. You know, check yourself. As the great philosophers have said, you should check yourself before you wreck yourself. It's true. Okay, so now, all right, that's really 20x, 2 plus 18, and minus 12 plus 42 is 30. Okay, so that's the derivative, always defined. Well, so what are we going to do? We'll plug in, set it equal to 0. Okay, so when does this equal 0? Aha, that's the same as saying 20x is negative 30, or x equals negative 3/2. So that tells us our x value. Great. How do we get our y value? Well, y is 3 times x plus 7. Now, that's negative 9 halves, and 7 is 14 halves, and negative 9 halves plus 14 halves, also known as 5 halves. So, our nearest point will be negative 3 over 2, comma, 5 over 2. Okay. Now, it doesn't ask for it. Doesn't mean we're not going to do it. How do we know it's the nearest? How do we know it's a min? Well, let's do a second derivative test, because look how clean our first derivative looks like. So our second derivative is going to be really clean. It's 20. And when the second derivative is positive, we look like this. So by the second derivative test, we do know that we have in fact found the point which is a minimum. We found a minimum. And because we only found one, it's got to be the minimum. And so life is good. We found the minimum. Woohoo! Yay us! We're awesome. Suppose for a differentiable function g of x, we have g prime of x is x over 4 minus 2 cubed times 4 minus x. And we have to identify and classify the critical points of g and give the inflection points of g of x. Okay, now you'll notice we don't actually know what g is, because what do they give us? They gave us g prime right from the start. Ah, wow, cool. So that's some good news for us, because that tells us we can jump in and start to do this portion, right? Identify and classify critical points, because that's really g prime type stuff. And you might say, well, wait, what about the other things? Well, the inflection points, we're going to have to hold off, because that's really a g double prime type stuff. We should handle the g prime stuff first. All right, so where to begin? Well, let's start by rewriting this, because I think it could be written in a more elegant way. And this happens a lot, right? That we have something not elegantly written, and so we say, let's work on rewriting. And what does that mean? It means algebra. Oh, 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 algebra. Yes, because what is algebra? Ultimately, algebra is the art of rewriting things to make them simpler. That's it. That's algebra. So we say, okay, what are some things we can do? Well, we can start by saying, I don't like this fraction here. So let's pull it out, and we'll do it inside of it to begin with. 1/4 times x minus what? Well, we pulled a 1/4 out. So if you pull 1/4 out from 2, what do you have? So to pull out a 1/4 is the same as to divide by a 4th, or if you like, to multiply by 4. So this becomes x minus 8 cubed. Now, the 4 minus x, that's okay, but I like to put the leading term have a positive coefficient. So let's pull a minus 1 out. So this is minus 1 times x minus 4. So, well, 1/4 cubed, 64 downstairs, and then there's the minus 1. So this would become minus 1 over 64 times x minus 8 cubed times x minus 4. All right, now that's looking pretty good. That's looking really good, actually. I like this. I like it. Now, what are we going to do? Well, we're looking for the critical points. It's polynomial. We love polynomial. And we say, okay, it's never undefined. We don't have any kind of boundary conditions or anything like that. So we say, well, let's set it to 0. Okay, so we set it to 0. And we say, well, there's sometimes when we do get zeros here, we get x equals 8 and x equals 4. Okay, so we sketch 4 and 8. All right, so what's our goal? We're trying to figure out the signs. So we plug in points. Well, something below 4, 0. Negative at the start. Negative 8 cubed is negative. Negative 4 is negative. So we have negative, negative, negative. 3 negatives. So that says G prime will be negative. Okay, how about between 4 and 8? Let's say 5. So that'll be negative. 5 minus 8 is negative. Cube that, still negative. 5 minus 4 is positive. Negative, negative, positive. Okay, so that's positive. How about above 8? Well, say 9. Negative. 9 minus 8 is positive. Cube is positive. 9 minus 4 is positive. So negative, positive, positive. Altogether, we are negative. So, what is it telling us? Well, we're figuring out, are we going up or down? And so in particular, we say, oh, we're going down before 4, up after 4. So going down, then up. What's the shape that's doing this? That tells us we are a local min. How about at 8? We're going up, then down. So going up, then down. Right. Up, then whoa! So what are we? Local max. Okay, so when it comes to critical points, we'll mark it here. Critical points, we have 2. At x equals 4, we are a local min. And x equals 8, we are a local max. Okay, so good. We've now done identify and classify the critical points using G prime, and they gave us G prime. But now the inflection points. Okay, so where do we get inflection points from? G double prime. All right, well, so we should find G double prime. So G double prime of x, we're going to take the derivative. We have our constant. And now it's a product of two things. So, okay, product rule. Derivative of the first term, 3x minus 8 squared times the root of the inside, which is 1, times the second term. So derivative of the first times the second, plus, we still have that negative 1 over 64, and then we have the first, x minus 8 cubed, times the derivative of the second, which is 1. Okay, let's clean this up. Well, they both have negative 1 over 64. They both have x minus 8. In fact, if you look, they both have x minus 8 squared. So let's pull that out. X minus 8 squared. Now, let's see, what's left? From the first term, we have a 3 and an x minus 4. So a 3x minus 4. From the second term, we've got the negative 1 over 64. We've only got 2 out of the 3 x minus 8s. So there's still an x minus 8 left. Oh, okay, well, all right. Let's see. This would become 3x minus 12 plus x minus 8. That's 4x minus 20. Okay. Oh, we can pull a 4 out. So let's pull a 4 out. All right, this is 4 times x minus 5. And pull a 4 out. So negative 1 over 64 times 4 is negative 1 over 16. X minus 8 squared, x minus 5. Okay, now that's our second derivative. So we're looking for inflection points. Now, inflection points are, you're kind of thinking of them as like critical points, for a second derivative. So you're like, okay, so looking for zeros and undefined. Never undefined. So we're looking for zeros, right? Yes. So where are the zeros? G double prime of x equals 0 at, well, x equals 8 and x equals 5. So are these our critical points? Maybe. Maybe. But not guaranteed. So here's the issue. Sorry, I said critical points. Inflection points. Are these our inflection points? Maybe. Maybe. What's the issue? The issue here is, what does it mean to be an inflection point? It means we are changing concavity. Okay, so we're looking for where concavity is changing. So with that in mind, if I have a critical point for the second derivative, it doesn't automatically mean concavity changes, because it could stay the same on both sides. So you have to test. So we're going to do a test. We're going to mark 5 and 8. Okay, so we pick some numbers, something less than 5. Say 0. Negative 8 squared is positive, and then negative. So negative, positive, negative. So we are concave up. G double prime is positive. All right, something bigger than 5, less than 8. Let's take 6. Negative 6 minus 8 squared is positive. 6 minus 5 is positive. So here, G double prime is negative, concave down. So this is good. Something bigger than 8. Say 9. Negative 9 minus 8 squared, positive. And 9 minus 5 is positive. Negative, positive, positive. And notice, we're still negative. So 8, this is not an inflection point, because the concavity does not change. But 5, the concavity does change. So this is an inflection point. Okay, so the punchline is one inflection point. So the inflection point is at x equals 5. Just the one. So be careful. Be the right amount of careful. All right, and there we go. There we go. We did it. We did it. We got to the end. Woohoo! Yes! All right, well, I hope you're enjoying this part of the course. It's very different, right? If you think back to where we were a few weeks ago, we were like limits and these rules, and we're like, this is so abstract. But now we're into this interesting part of the course, like applications. How are things changing? How do we get the most out of our resources? And qualitative, we're going up, we're going down, concave up, concave down. This is the good stuff. I hope you're enjoying it. And thank you so much for your hard work. Let's celebrate. High five. Yeah! Keep it up, and I hope to see you again. Booyah!